The broadcast is now starting. All attendees are in listen-only mode.
Hey everybody, welcome back to Young Engineers of Today. Hey Cohen, sorry about the delay there. I had to get some things handled before I got started. We don't know who won the bridge contest yet. Matteo? Believe Mr. Dubik is still taking submissions until tomorrow. Hey, so I don't know yet, but hopefully we should know soon. Here, we shall see. But yeah, so welcome back to Young Engineers of Today. Welcome back to Fly to Learn. We're actually going to do lesson 3. And we're going to probably just get as far as lesson 3. Maybe we'll hit some lesson 4 today. I don't know. We'll see. The reason I say that is because things are going to work a little bit differently this semester as far as Fly to Learn is concerned. I don't think you guys did Fly to Learn last semester. I think it was last year. But anyway, if you've done it in previous years, you've known that we've sort of run through the lessons. I kind of walk you through how it's done, and then we go, but, do it on your own time later. That's not really going to be what we're doing this year. Basically, we're going to run through the lessons. I'm going to walk you through how to do it, and then you guys are going to do it here during class. The reason for that is, we tried to stick to the whole, not having you guys have to do stuff outside of class because it kind of technically becomes homework, which sort of kind of goes against what we've been trying to, do, which is avoid homework and not give you guys more work than you probably already got from all your classes and stuff like that. And on top of that, if you guys have any questions about anything while you're running through it, I'll be here to help you out with it. So to that end, we'll be, doing it during the class. Also, on top of that, based on those things combined, people didn't really tend to do the lessons outside of class. So we ended up just sort of running through things, and you're building upon a foundation that wasn't really there. So yeah, we'll run through the lessons during class. This is going to slow down the pace probably pretty significantly, and things might work a little bit differently between when Mr. Dubik does the class and when I do the class, just by virtue of the fact that we're going to have sort of different paces on it and stuff like that. But we'll try and get at least you guys through lesson 3 today. Hopefully, get started on lesson 4. We'll see how it goes. But lesson 3 should be pretty short. Lesson 3 is about lift. So lift is a force that helps pilots and engineers overcome weights. Lift is what makes you go up into the sky. If you lose lift in flight, your aircraft will fall out of the sky. You'll fly like a rock, basically, or a brick, or a sandbag, or whatever. Insert your favorite heavy object that doesn't actually fly here. That's how your plane will work. Yeah, making it a rocket, not a plane. If you don't have any lift, you're not flying. It's just not happening. Which is why, you can't exactly stick wings on a rocket to make it fly better. Now, I say that, and there was the space shuttle, but the space shuttle used its wings for when it got back. Because an essential component of lift is, air. So wings don't really work in a vacuum, which is why you've got capsules like the Dragon and the Apollo and Gemini and Mercury missions and things like that. So force is a push or a pull. It is composed of a magnitude. I know I kind of jumped ahead here, but force is a push or a pull. It's composed of a magnitude, which is how large the force is, and the direction of the force. A magnitude and a direction is a velocity, or a vector, excuse me, it's a vector, but it's also a velocity, if it's a speed. I misspoke. So a vector. A magnitude and a direction is a vector. We represent forces by drawing vectors, which are arrows, which tell us the magnitude and the direction of the force. The reason why we use arrows is because arrows are very good at telling us not only a direction, but also a magnitude. If it's a bigger arrow, it's got a higher magnitude. If it's a smaller arrow, it's got a lower magnitude. Magnitude is simply just a fancy name for strength, in essence, sort of, mostly. You can think of it that way. Like, when you think of the Richter scale, um, say, oh, it's a magnitude 6 earthquake. You're like, oh, wow, that's pretty bad. And they go, oh, it's a magnitude 8 earthquake. And you go, wow, that's really super bad. Because you know that a magnitude 8 is stronger than a magnitude 6. And the Richter scale, if I remember correctly, it's roughly 100 times stronger, which is just absolute bananas. But anyway, point is, uh, magnitude is essentially another name for strength. Strength and direction makes an arrow, which represents a vector, which is what a force is, because a force is a direction and a magnitude. The specific force we're going to be looking at here is lift. So the direction of lift is up, and it's going to be perpendicular to the flight path. So if our plane is, here's our plane, here's its little propeller, here goes the plane. Look at that wonderful looking plane. So if the plane is flying in this direction, lift is going to be in that direction. Conversely, if the plane is flying upwards, then lift is going to be kind of towards the ground. If the plane is flying downwards, then lift is going to be up in the air. So lift is always going to be perpendicular to the direction that the plane is moving in. The amount of lift is very sensitive to the speed of the air traveling over the wing. When there is not enough air traveling over the wing, lift suffers and the plane begins to fall out of the sky, or it stalls, because lift results from the differences in air pressure. So lift is directly north to whatever the direction. Yeah, basically, like if you wanted to think of looking at the plane from the side, lift would be north. If the plane was always facing, whatever, west or east, lift would be north. Again, this is, looking at it from the side. So, yeah. In essence, lift relies on a mechanism that is still kind of argued about by aerospace engineers, amazingly, or aeronautical engineers, even though we can get it to work. Basically, it's a function of air pressure mostly. The idea being that there's a bunch of wind hitting the wing of the plane, which is sort of forcing the wind upwards. So as the wind bounces off it, pew, pew, equal and opposite reaction, the wing kind of wants to go up this way. As the plane is moving this way, kind of forces this arrow to move more in like this kind of a direction, which means that the plane is going up into the air. The other idea with this is as the wind travels underneath it and travels over it, the wind that travels over it has to travel faster. So the wind that's traveling over it, since it's traveling faster, it's going to have lower pressure. Since the wind underneath it is traveling slower, it's going to have higher pressure. And anything ever is going to want to naturally move from a position of higher pressure to a position of lower pressure, and thus the wing moves upwards. So that's sort of the other school of thought as to how wings work. And I think the truth lies somewhere in the middle, if I'm, the general consensus is to be believed. But anyway, let's go ahead and get X-Plane started up. Boop. That's the installer. Run the X-Plane 10 demo. There we go. Run the demo. Shiz. I just want to run the demo. So this will take a minute. Or not. All right, so general aviation, Cessna 172 SP, like you do, daytime, clear, fly with these options. Now this one is going to take a while. Cessna 172 SP taking off from Seattle Tacoma Airport in clear daytime conditions. Oh, buddy, this always takes a while. We'll just let it do its thing while it loads the scenery files and loads planes it's never going to use, like the space shuttle. Seriously, though, I watched that happen last time. It was like, loading heavy metal space shuttle textures. I'm like, why are you doing this? There aren't going to be any space shuttles flying around. Finishing asynchronous loading. Let it take its time, here it goes, taking its time, loading. Now, it makes me sound more bitter about it than I actually meant to, but I just wanted to make a song about it. It's loading the King Air. There's the C-130. Looks like it's just loading an aircraft file, so maybe it's not necessarily the texture. Okay, so we paused it immediately. Yeah, we're going to be taking off from runway 16. All right, so if we go up to the top here and under location, we could select global airport. KSEA. We're going to select Seattle Tacoma International. Look at those nice straight runways there. As you can see here, we've got runway 16. We got a few of them here. 16C, R, and L. Let's do, I guess, L. Because they're, but we're going to select the final approach, which is 3 nautical miles. That's what NM is, not nanometers. We're not, literally about to touch the ground. We're 3 nautical miles away. So 16L, 3 nautical miles. It's going to reload real quick like. And now we're going to be in the air and paused. And there is our runway. Be ready to press P to pause the simulation. Now, hopefully yours starts out paused. Then we're going to go to data input and output. We're going to go up to settings then, and data input and output. And here's this screen, which is kind of a little mess, but that's okay. We're going to have some very specific checkboxes checked. So what I'm going to do up here in the upper right-hand side of this window, I'm going to click Clear All in order to get rid of all of these. And I'm going to click some checkboxes next to some values. That was vague. The airport is going to be Seattle Tacoma, so KSEA, Kilo Sierra Echo Alpha. If we're going to use the NATO phonetic alphabet. KSEA, let me go back to that one real quick. Location, select global airport, Seattle Tacoma International, and then we're going to do the final 3 nautical mile approach to runway 16L. Boop. Like so. All right, so yeah, settings, data input and output. So what do all of these checkboxes mean? Well, that's a good question. So each of the checkboxes in a row, well, excuse me, next to a value represents the value that it's going to be tracking. The first checkbox, if you check it, will send data to an IP address. The second checkbox, if you check it, will send data to a text file. The third checkbox, if you check it, will send data to this graph here under data C. And the fourth checkbox, if you check it, will place the data directly into the upper left into a little heads-up display over here when we get back to the plane. We want to output it to a graph and to the screen. So we're going to check the last two checkboxes on each of the values that we're interested in. In this case, it's going to be speeds because we want to know how fast we're going. So we're going to check the last two checkboxes there, which is going to be graph it and put it on screen. And then the other one is going to be way over here on wing lift. So number 92, we're going to check the last two checkboxes on it. So we've got speeds and wing lift. Once I've got these two data sets checked, or excuse me, recorded, like data points checked, whatever, data feeds checked, blah, I'm going to go ahead and click the X. And so we should see up here, we've got velocity, or V. Yeah, I guess it's velocity. Not technically, velocity is a speed in a direction, but whatever. And then we've got wing lift. Right now, they're all reporting 0, more or less, except for the vtrue ground speed. So we've got vtrue knots. KT is for knots, KNOTS ground speed, and vtrue miles per hour ground speed. Knots are simply just the nautical speed unit. So you got ground speed, you got airspeed, and then just general velocity. What we're interested in is, well, we're interested in checking out the oh yeah, we're interested in checking out the airspeed and the lift. And there's one final thing we need to do in order to view the lift. So now that we've shown the test data, we're going to show the lift vectors. So under special over here, we've got show flight model and output flight model. We're going to click on show flight model, which now we've got a checkbox or check mark next to it. And if I hit Shift 8, well, you can't really see anything right now, but if I unpause it and repause it really quickly, you'll see all these little green sort of lines that come off of it, as well as these white lines here. So the green lines, my pilot, very self-assured. The green lines represent the lift, basically the pull upwards on the wings. Well, they're actually just the forces that are exerted on it, because you can see some of the green lines are going downwards here. So the green lines are the forces. The white lines are, so in essence here, the propellers are spinning. So the white lines show the direction that the propellers are spinning, and then the green lines show that the airplane is being drawn forward on each of these propellers due to it. So now we've got our forces data on the plane. Yeah, white line should be projecting onto the propeller. These represent lift. Okay. Finally, we're going to change the payload weight to 296 pounds. And the reason we're doing that is for consistency's sake. Since the last test, our control was 296 pounds. This time, our control is also going to be 296 pounds. So we go up to aircraft, and then weight and fuel. And under the payload weight, we're going to drag this up to 296. Why 296? I don't know, but that's what it is. We've got a payload weight of 296 on our wee little airplane here. If you're not in chase view, press A, and then press Shift 8 to circle around the plane. So, well, turn that off. So now we're checking out our aeroplane. And this is all the necessary setup we want to do. So now we need to actually perform the test. So fly the plane level for 3 seconds, then watch the green lift arrows on the wings and the V-true airspeed in the top left corner of the screen. Then you're going to want to put the plane in a 3-second climb and then pause the simulation, but do not change the throttle. We want to see what the airspeed does as you climb and what the lift arrows do as you climb. So let's go ahead and click in order to bring up our little control. Unpause. 1,000. Yeah, understood. Oh, we want it to. Come on. There we go. Okay, so we want it to fly forward for 3 seconds. 1,000, 2, 1,000, 3, 1,000, and then fly upwards for 3 seconds. 1,000, 2, 1,000, 3, 1,000, and pause. And if we go up here to settings and then data input and output and look at our data C, we can see that we can check our lift here. The lift goes up. So as you can see, we've got kind of like this nice like peaks and valleys thing kind of going on with each of these. But what we're interested in is the last 3 seconds here. As you can see, as we tilt up, first off, the lift starts to go crazy. Then it kind of goes down, then it kind of goes up again, and then we see it steadily go down because we start to bleed off speed. You can check out the V true, and you can see that it goes up and then down. And the down, actually, it looks like this is where we start to tilt up. So you can see right about here, we start to bleed off speed, and we get a nice boost in lift for a second, and then it starts to drop off. This is because this is where we tilt up. So we start to lose speed at a fairly steady rate, and the lift starts to drop off as well. Then we're going to continue climbing until the lift arrows nearly disappear, but do not change the throttle. And then check out, again, the graph, see what's going on, check out the airspeed, continue the simulation, see what happens to the plane. Then we're going to force the plane into a stall. This is what's going to happen shortly after we do what is described here, which is to continue climbing until the lift arrows nearly disappear. So the plane is going to go into a stall. We're going to see the stall happen, and then you're going to recover from the stall, which is basically just pointing the nose down until you regain enough speed in order to get lift again. So I'll go ahead and let you guys play around with that for a few minutes here. Once that's done, once you've done that and checked all that out, go ahead and raise your hand, and then we'll continue. Excuse me. And in fact, just go ahead and fly and stall and recover a few times and watch the lift arrows. All right, and if you're already done and your hand is raised, that's fantastic. Just go ahead and do a little bit of free flying. All right, just waiting on a few more people. No rush. I just wanted to let you guys know the situation. It's not like I've forgotten about you or something. You get back to the cockpit by pressing W on your keyboard. Yeah. Ooh, yeah. We'll just go ahead and do some wicked stunts. Hmm. I feel like you shouldn't be, what with the plane and all. Ah, yeah, that happens. Doing all right. How about you? Good, good. Glad to hear it. Keeping busy? Whoop, crashing my plane. You keeping busy? Yeah, I hear you. I hear you. I remember high school being pretty much defined by that. And then it really didn't get any better in college. Oh, yeah, yeah, yeah. All right, fair enough. Chapel Hill for a degree in computer science? Yeah, I'd say so. That's actually, and truth be told, never completed my degree there, but that is what I spent a few years doing. I ended up getting a job in the field that that I'm interested in, and so that's what I've been doing. But yeah, no, it's going to be a fair amount of work, but it's a good school for computer science. Definitely, it's very well respected. You trying to graduate earlier? Oh yeah, yeah, I get you. Yes, I do. Actually, living in Chapel Hill right now. Yeah, yeah. I used to do the summer camps in Raleigh for young engineers that were like Minecraft camp and stuff like that. And then I'd pop down to Charlotte for a while to do the ones down there, and that's what I used to do with my summers for young engineers. I enjoy it. It's great. It's great fun. All right, so we got pretty much everybody ready to go here. So yeah, test piloting should show you guys that lift is directly dependent upon airspeed and you're facing and stuff like that. Lift is also dependent upon the angle of attack. Hey, look at that next sentence. The angle of attack refers to the angle that the airfoil makes with the direction of the airflow. This explains the fact that in a dive, the airspeed was increasing, but there was very little lift generated until we pulled up the nose. Then, with both a better angle of attack and airspeed, the lift vectors rose dramatically. You would actually see on the plane itself when you were checking it out. I mean, obviously you can't really see it right now because the plane isn't flying. But if I were to put in the throttle here and start trying to take off, and then doing some dives and nose up, some dives and climbs. Excuse me, that's the word I was looking for. You'll see that the force exerted on the wings will actually just increase a lot when you speed up. But yeah, so in order to actually gain altitude, we need to take advantage of that angle of attack so that it provides a counter force to gravity. Yeah, I believe it. The X-plane demo thing is pretty brutal. It's part of the reason why you wanted to do that angle of approach, 3 nautical miles from the runway, as opposed to trying to take off the ground. Makes it easier. So, what is lift? We've learned about the impact of airspeed and the angle of attack on lift, but what is lift? Well, lift is the result of a difference in air pressure. The pressure on the top of the wing is less than on the bottom of the wing. Most scientists and engineers agree on this point. Most, you see the most there. Um, there's some out there that apparently don't subscribe to that, which, all right, give them points for creativity. I will say that I don't know everything about this, and so there are theories that were laughed at in the time that came to be accepted later. So you never know. I guess it's important to keep an important, or excuse me, a healthy critical eye when looking at scientific theories and making sure that they make sense scientifically speaking. So anyway, nice little aside for most scientists and engineers agree on this point. I feel like it's a pretty widely known thing. So anyway, what causes the difference? Well, listed below are several explanations. This is where it gets to the point where it's a little bit more fractured as far as what actually causes the difference. So there's the longer path or equal transit theory. The air flowing over the top of the airfoil travels faster than the air underneath the bottom of the airfoil, and the airfoil is a curved shape. Therefore, the air molecules traveling across the top travel a longer distance than those on the bottom. As a result, the air molecules spread out and travel faster on top than the air flowing on the bottom of the airfoil. I think just yelled at me for having a loud microphone level. I'm sorry. I didn't realize I was talking so loudly. Geez, GoToWebinar. Make me feel more self-conscious about my voice level. So as the air molecules move over a greater distance, they move faster, which creates a sort of a lower pressure pocket on top of the wing. This is also sometimes known as the Bernoulli principle of lift. So yeah, as the air particles move faster, they create a lower pressure zone, and the wing wants to move from high pressure to low pressure, so you go up. The skipping stone theory. Due to the angle of attack, the airflow strikes the bottom of the wing and bounces off. The resulting force is lift. This is also known as Newton's third law. All right, so these are basically the things that I was just talking about. So then we've got lesson 4. Exciting. We hit lesson 4. Drag. The Wright brothers were engineers first, pilot's second. This is my my Civ reader impression, being Sean Bean or Leonard Nimoy or whatever, reading off of the little technology quotes every time a technology is researched in Civilization. It's a terrible impression. Anyway, in this lesson you will learn about drag. So drag is the force that resists the movement of the airplane through the air. So this is the opposite of thrust. Drag slows down planes, and drag results in lower fuel economy. Generally, engineers design planes to reduce drag. So this is one of those wacky things. Drag is a result of friction from air. Drag makes a plane slow down. These people need to stop having a conversation. My computer needs to stop telling me. In a bit of an annoying little quandary, though, is that the friction from air and the fact that air exists is kind of what causes lift as well. Like we could eliminate drag entirely by not having air. Well, not entirely. We could eliminate drag entirely by not having by existing in a perfect vacuum. Unfortunately, that plane would never take off. It would never go anywhere. The same I wanted to say molecules and particles at the same time. So I came out with polycules. I hope that's a fun new word. The air polycules that thrust takes advantage of in order for the plane to move forward, and that lift takes advantage of in order for the plane to go up, also work against it with drag. So it's kind of a, give and take kind of a thing. So force is a push or a pull. It is composed of a magnitude, how large the force is, and the direction of the force. We represent forces by drawing vectors, which tells the magnitude and the direction of the force. Yes, we've got all that. Drag is directed along and opposed to the flight direction, or the thrust direction. Drag is a force that resists the movement of the airplane through the air. Drag is unavoidable. The good news is we're going to fly a new plane. So, unfortunately, we can't avoid drag. Fortunately, we can fly a different plane. So let's check out our sweet new plane. We're going to keep the same airports. We're going to keep the same flying conditions. We are going to be flying a King Air C90B. So the King Air C90B is going to have 2 engines. 2 engines means more power. It also has retractable landing gear. So same deal. We're going to be flying out of Seattle in clear conditions during the daytime. However, we are not going to be starting from the ground, just like before. We're not going to be starting from the ground. We're going to be starting from in the air. It is going to be the final approach, or the final landing, at 3 nautical miles. So let's wait for this to load. There we go. Look at this dang plane. Look at this dang old plane. There's a lot to check out here. We got our chronometer here. I don't understand how it is 8 o'clock, 8 p.m. and super duper bright. I guess, it is pretty far north, so I suppose never say never. But hey, let's hit Shift 8 real quick and take a look at this thing. Look at this sweet plane. This thing's pretty awesome. We'll hit W again to bring us back into the cockpit. And rather than worry about the whole takeoff sequence, we're going to go up here to location. We're going to select a global airport. And under runway 16, we're going to select 3 nautical miles. Make sure as soon as it loads, it's paused, because that's going to be super important. Cool, minus paused. Excellent. Shift 8. We admire the situation that our plane is in as it's flying through the air. We'll unpause it real quick. There we go. Just wanted to let everything sort of register for a second, the propellers to turn on and register their forces, and the wings to register their forces. And let's go ahead and pull up our data. So we're going to click the last two checkboxes at speed and click the last two checkboxes at landing gear deployment. So we'll go up here to settings, data input and outputs, data set. So we're going to uncheck wing lift, and we're going to check landing gear deployments. So 67, the last two checkboxes. When that's done, pause. We can hit G in order to deploy or undeploy our landing gear. And what we're going to do is we're going to check out the airspeed after flying the plane level for 3 seconds. Then we're going to lower the landing gear and then fly the plane level for 3 seconds. And so on. Basically just do it 3 times in order to get accurate data. So 1, 2, 3. Let's line it along the back of the plane. There we go. There we go. And lower the landing gear. And once it's lowered, 1, 2, 3, and then re-raise it again. And we'll go up here to our data input and output and check our sweet graph here. And as you can see, we've held more or less steady. In fact, we've gone faster. All right. So apparently, I was not holding the plane level. Let's check this out. Let's try and hold the plane a little bit more level. So you've got a all right, there we go. Now we should see it happening. Now we're seeing the speed go down. Now let's bring up the landing gear. And we'll watch the speed go back up. All right, now we'll check the data input and output. Okay. Something wonky is happening here. All right, so my data isn't displaying correctly. That's okay. We get the idea. If we watched up here in the corner, you could see the speed going down and then back up as you lowered and then raised the landing gear. Also, apparently 11 minutes have passed. 3 minutes have passed. Just 3 minutes. What am I thinking? 3 minutes have passed. Also, this plane is pretty dang fast. Anyway, point being, the landing gear raises the drag, and thus the plane begins to slow down and have to work harder. But that's going to do it for today. So if you have, basically, we're going to call it a day here. We're going to do the poll questions. If you have any questions about anything after the poll questions are done, I'm here. Otherwise, you're more than welcome to head out after the poll questions, and have a wonderful weekend.